Welcome to the Explainer. Today, we are diving into a really cool family of organic compounds, alcohols, phenols, and ethers. Now, these guys are everywhere, and they all share a connection to one single, incredibly important element. So, think about it for a second. You've got rubbing alcohol, you have powerful antiseptics, and even old-school anesthetics. What's the link? Well, it turns out their amazing and very different properties all come down to the presence and, crucially, the placement of a single atom, oxygen. All right, let's get right to the heart of it. The key player connecting our first two compounds is something called the hydroxyl group. You'll see it written as a -OH. And this little group right here, it's the whole reason alcohols and phenols get their names and, a lot of their signature moves. On paper, it looks pretty simple, right? It's just an oxygen atom bonded to a hydrogen atom. But here's the twist. Where you attach it changes everything. Stick that negative OH group onto a regular saturated carbon chain, and congratulations, you've made an alcohol. But attach that exact same group directly to a special kind of structure called a benzene ring, and its whole personality flips. Now you've got a phenol. So let's start with the most familiar member of the family, the alcohols. These are some of the most versatile and common organic compounds out there. We're talking about everything from the ethanol in a glass of wine to the rubbing alcohol in your first aid kit. So chemically, what does that mean? Well, an alcohol is basically any organic molecule where that hydroxyl, that -OH group, is bonded to a saturated carbon. Chemists have a shorthand for this. They write it as ROH, where that R is just a stand-in for, the rest of the carbon molecule, whatever it might be. Okay, but not all alcohols are created equal. We actually classify them into 3 degrees, and it all depends on the carbon that's holding onto that OH group. If that carbon is only attached to one other carbon, we call it primary. If it's attached to 2 others, it's secondary. And if it's crowded in by 3 other carbons, well, that's a tertiary alcohol. And this isn't just a random detail. It completely changes how the alcohol is going to react. Ever wonder why ethanol boils at a balmy 78 degrees Celsius? But propane, which is about the same size, boils way down at -42? The secret is something called hydrogen bonding. That little OH group acts like a tiny magnet, allowing alcohol molecules to stick to each other really strongly. This makes them harder to boil, and also helps them dissolve super easily in water. And this brings us back to why those 3 degrees are so important. It's like a chemical personality test. If you try to oxidize them, a primary alcohol will first turn into an aldehyde and then into a carboxylic acid. A secondary alcohol, it'll turn neatly into something called a ketone. But a tertiary alcohol, it pretty much just sits there and refuses to react. It resists oxidation. So we've got a handle on alcohols. Now let's meet their more intense cousin, the phenol. This is what happens when you take that same hydroxyl group and introduce it to a whole new environment. You give it an aromatic twist. And here it is again, that one critical difference. Instead of our ROH shorthand, we now have ROH, where that R stands for an aromatic ring, like benzene. Bolting the oxygen directly onto that ring totally rewrites the chemical rulebook. And here is the biggest change in personality: acidity. Alcohols are about as acidic as plain old water, which is to say, not very. But phenols, they are way more acidic. In fact, they're acidic enough to easily react with a base like sodium hydroxide, something a regular alcohol just won't do. So why the huge jump in acidity? Well, it's all about stability. First, that big benzene ring is really electron hungry, so it yanks electron density away from the oxygen. This weakens the bond to the hydrogen, making it easier to pop off. But here's the real magic. Once that hydrogen leaves, the negative charge left behind on the oxygen doesn't just stay put. It gets shared and spread out all over the entire benzene ring. Think of it like sharing a heavy load among many people. It makes the whole thing incredibly stable. Okay. We've seen the reactive OH group in action in both alcohols and phenols. So now let's meet the third member of our little family, the ether. And if alcohols and phenols are the reactive siblings, then ether is the calm, stable one. So, structurally, ethers are a totally different ballgame. There is no OH group. Instead, you've got an oxygen atom that acts like a bridge, linking two carbon groups. We write this as ROR prime. And that missing hydrogen on the oxygen, that makes all the difference in the world. Because ethers don't have that OH bond, they can't do that hydrogen bonding trick we saw with alcohols. The result, their boiling points are way, way lower. It also means they're pretty unreactive and chemically inert, which, it turns out, makes them fantastic solvents. They can host a chemical reaction without getting involved themselves. So how do chemists make them? Well, the gold standard method is called the Williamson's synthesis. It's a clever process where you basically take an alcohol, make it more reactive, and then use it to attack another carbon chain. It's a really efficient way to just snap those two pieces together with that stable oxygen bridge right in the middle. All right, we've met all three of them: the workhorse alcohol, the acidic phenol, and the stable ether. Now let's pull them all together, side by side, so we can really see what makes each one tick. This chart really lays it all out. You can see this perfect chain of cause and effect. It all starts with the structure. Is it ROH, ROH, or ROR prime? That one choice directly impacts everything else. Look, because alcohols and phenols have that negative OH group, they can hydrogen bond, which gives them high boiling points. Ethers can't, so their boiling points are low. Same story for reactivity. That exposed negative OH group is a reactive hotspot. Ethers tuck their oxygen away in a bridge, making them stable and pretty unreactive. It all connects. So, what's the big takeaway from all of this? It's that the chemical neighborhood of that single oxygen atom dictates the entire personality of the molecule. Is it attached to a simple carbon chain, an aromatic ring, or is it sandwiched between two carbons? That one simple fact changes everything about how it behaves. And that really leaves you with a final question to chew on. If just changing the neighbor of a single atom can create such huge differences, turning a solvent into an antiseptic, it kind of makes you wonder, doesn't it? How many other things in our world are defined by a similarly small but incredibly profound twist of chemistry?